Hey, thanks for tuning in to hopefully see the rest of the presentation on mathematics and spirituality. I hope that you found the first part interesting. And it was all about kind of a history lesson on number systems in general. And now I want to make the connection to um, number systems, the expansion of these number systems to spirituality. You might have already kind of picked up on the theme that I was getting at, which is that both math and spirituality are this exploration of things into the unknown. And unfortunately, the way that most of us learn math is very much learning, following the path of people who came before us. So we're not really discovering anything. We're just learning the rules that other people discovered. But at a foundational level, that's what mathematics is. It's learning these rules, it's finding these proofs so that we can make sense of the world around us. So, something that really inspired me to make this presentation, which was just for presentation night with my friends, and I got way too excited, but was this podcast where I was listening to Edward Frankel, a Russian mathematician, being interviewed by Lex Friedman, sent to me by my therapist. It's like 3 hours long, and I loved it, reignited my passion for math, even though I don't get to do a lot of math that I think is more interesting these days, teaching at a community college. I'm kind of sticking to, the content that I get to teach. So it was really cool to listen to this guy talk about math. He wrote this book, Love and Math at the Heart of Hidden Reality. And essentially, the takeaway that I got from his talk was that we live in this world full of paradoxes and that mathematics requires creativity and sometimes the way that we think about the world needs to be adjusted, right? The same way that we used to not have negative numbers until we started using negative numbers, and now that's something we take for granted. We used to not have the real number system until we discovered irrational numbers. We didn't have complex numbers until someone was willing to take the square root of a negative number and see what happened. Right? So he's saying that we think that we have this understanding of the universe. Many people like almost have this religion of science in and of itself, but we are completely ambiguous, and that some of these ideas that we have can't really explain everything and or might need to be adjusted. Right? I apologize that I don't have his exact quote. The podcast again was very, very long, but that was kind of the takeaway that I got is we live in this world full of paradoxes, right? And this jump from things being discrete to continuous. So the jump from the rational numbers to the irrational numbers to me is a huge deal. So we live in the world of both the discrete and the continuous. Right? So what I mean by that is we are discrete, countably infinite, right? I can count the number of fingers I have on my hand. I can count how many students are in my class. We are discrete, separate, countable individuals. But at the same time, we all interexist. We are all continuous in terms of our consciousness, right? I can't exist without the entire society around me kind of helping me to exist. Who creates my food? The trees create the oxygen that I breathe. The sun gives them the energy to survive. I give them carbon dioxide that they need. And like we're all part of this continuous, ever changing, ever expanding thing that we call life. We are both in the infinite and the finite, right? Finite in the sense that we come into existence at some point, right? Depending on your beliefs. And then eventually we die, and whatever, I am Scott, whatever we define as Scott will eventually end. However, we are also, again, part of this infinite, forever progress that never is ceasing, right? I can't exist without all of my ancestors. And at the same time, if I ever have kids, they won't exist without me having existed at the same time. All right, so how does this connect to math? And again, it has to do with everything from the jump from the rational number to the real number line, going from things that are countably infinite to uh, to uncountably infinite? How do we go from individual separate things to this smooth continuous line? It's a huge, huge idea. Um, Another kind of way of thinking about this is like jumping in dimensions, right? The two-dimensional plane exists, and as soon as we add this third dimension, it opens up things and makes things incredibly complicated, and it's very, very difficult to grasp, like the infinitudes that live inside of this additional dimension. Uh, right, so it's very, very complicated. I made this connection when I was trying to teach my statistics class the difference between discrete random variables and continuous random variables. And that idea was abstract and very difficult. And I didn't quite grasp why, because it made sense to me. But it's because we're now trying to hold these two things at once, that the world can be, infinitely dense and countable, but um, also this smooth continuation. So if you ask somebody what's the probability that somebody's height is exactly 6 feet, it is a 0% chance, because if you're finding an area on this curve, the area is only has a single dimension, and the area of a single dimension line is zero. I don't know if you need an image for that. Maybe that's over some of your heads, but I've got some cool visual aids coming up that'll hopefully help illustrate some of the crazinesses that happen with infinity. That's kind of the big theme, is we have an infinitely dense number of numbers, fractions, and we're shoving an infinite number of new things inside those fractions, right? Infinity inside of infinity. Crazy. So these are some of the paradoxes that I think are incredibly fun, because we do live in this world where we have to grapple with infinity, both things that are infinitely large, expanding forever, and things that are infinitely small. If you are into the multiverse theory, infinity is for you. So, Hilbert's Hotel, there's several different levels of it. We're just going to go over a couple basic ones. So, imagine there's an infinite hotel, right? There, you go down the hall, you'll walk forever. Every single room is occupied. If you walk down the hall forever, you will never find a room that's open. However, there's also always a vacancy. How do you do that? You just make everyone get out of their room, move down one room, right? That will happen forever. And now the first room is wide open and you can move in and stay in the hotel. Yes, this would be a logistical nightmare, because every new guest that checks in means every single infinite number of guests has to move. But the idea is we somehow, with being infinitely full, can still fit another person in. So the question remains, all right, we get two people, move down two rows. What if you get an infinite number of guests, right? A bus comes on, and that bus is has an infinite number of people. So a new person's going to come out forever. We can actually fit all of these people into this hotel still. What you have everyone do is go to the room that is double their current room number, and now you have an infinite number of new open rooms. So person in room one goes to two, two goes to four, three goes to six. And so the first person off the bus goes to room one, next person off the bus goes to room three, next person off the bus goes to room five. And you can do that forever. Every single person will have a room, even though there was an infinite number of them. This is kind of this question of, are there more numbers or are there more even numbers? The answer is it's the same. Even though there are literally twice as many numbers as there are even numbers, um, it's also the same. Kind of a crazy paradox. That there's this infinity, again, nested inside of infinity. There's another complicated example where you have an infinite number of buses that arrive. Each of those buses has an infinite number of passengers, and you can still accommodate that. But I have other paradoxes I want to go over instead. So, this is that dimensional thing that I was talking about. When if we're making a leap from, I mean, it's sort of just a single point onto the first dimension, which is a line. Um, but again, it's now we have something that's continuous, and there's an infinite number. Uh, so even though we've got two continuous lines here, The top line is twice as long as the bottom line. So if I said how many dots, individual points, so like a single dimension or zeroth dimension dot, are going to be in the bottom line compared to the top, right? Sort of like the question, are there more even numbers or odd numbers? Or sorry, even numbers or numbers total? And they actually have the same number of points. And the way that you can prove this is you turn that long line up on its side, and now we have that one-to-one correspondence of every single dot in that top line to every single dot in the bottom line. So even though there's an infinite number of them and that top line is twice as long, they have the same number of uncountably infinite uh, points. Crazy. All right, one more. So a super task is where you are completing some sort of a task an infinite number of times in a seemingly finite interval. So this one's like one of my favorite paradoxes of all time, the Littlewood-Ross paradox. So what you're going to do is you put 60 seconds on the clock, and then with half of the remaining time, you will perform a task. So this is what lets us theoretically do something an infinite number of times. So you'll do the task at 30 seconds, then 15, 7.5, et cetera, et cetera. So you have to start doing the task faster and faster. But by the time you hit zero, in theory, you've done this task an infinite number of times, which is kind of wild because crazy things can happen if you do something an infinite number of times in a finite amount of space. So what you do is you put 10 balls into a jar, number them 1 through 10, and then you remove the smallest ball from the jar. So after the first task, you can see here, the first ball is out of the jar, 2 through 10 is in the jar. Second task, take out ball 2, and then you have balls 3 through 20 in the jar. Third task, take out ball 3, you have balls 4 through 30 in the jar. So the question is, how many balls are in the jar when you reach 0 seconds? And the answer is we don't really know. Most of us would probably say, well, there's an infinite number of balls in the jar. We're adding 9 each time, plus 9, plus 9, plus 9, plus 9. That's a great argument. And certainly there's some validity to it. However, on the other hand, I could say, okay, give me the number of a single ball in the jar. Right? You can't, because at some point I removed that number. 10 billion, I removed that at the 10 billionth step. Yes, we've added an infinite number of balls, but we've also removed every single numbered ball from the jar. So in another perfectly valid argument, you could say there are no balls in the jar. We've added 9 each time, but we've removed every single one of them if we've done this task an infinite number of times. So there's a couple more little paradoxes. I'll go through these very quick. First one is Zeno's paradox, which is another super task. So imagine that someone's racing a turtle, and the turtle has a head start. So the logic is by the time that person reaches where the turtle is at, the turtle will have moved a little bit. Then the person will, again, close that gap to where the turtle previously was. Right? So you can see here's where the turtle was when he starts. By the time he gets there, the turtle's moved ahead. He now needs to get to that distance. By the time he gets there, again, the turtle will have moved ahead. He will eventually have to get to that new spot, and again, the turtle will have moved ahead. So the question is, how could somebody ever win in a race, ever, if they don't have a head start? Right? And we know that this is somehow we're continuing through this, like pushing through this infinity, right? There's an infinite number of numbers in these small spaces, but we just live right through it. We pass right through it. The arrow paradox, if you look at motion of an arrow at any individual moment, right, a snapshot, it's not moving at all. There is no movement whatsoever, but it's this continuous flow that you can't capture in any individual moment, right? And so if we're trying to pretend that like we have these discrete moments in time, motion doesn't really exist, and yet obviously we're all moving all the time. This is essentially what I think calculus is about. How do you measure the instantaneous rate of something if if we're trying to divide by 0, right? We're trying to take a snapshot of someone's motion. I can't actually measure their speed, right, over an interval of 0. Calculus lets us do that, which is really cool and really, really powerful. So that's just the world that we live in, right? We don't often talk about it, not even in our math classes. We just kind of do the math. But it's like this is happening in the background all the time, right? So there are some people that truly think like science will eventually answer all of the questions, but like we are so limited in our scope that there are literally mathematicians who understand how systems would work in like an eight-dimensional existence, an eight-dimensional reality, even though we have no conceptual idea of what that would look like because we've done the math and we've been able to prove certain things. But of course, we'll never truly conceive of that eight-dimensional thing because we're limited to these three-dimensional human brains, right? Some things are definitely never going to be reconcilable, and that's okay. We have to live in these paradoxes. We have to sort of embrace that there's this unknown, and people don't like the unknown, which is why many of them turn to religion. Um, and that's why I kind of turned to spirituality is I don't know. The more that I learn, the more I realize I really don't know a lot of things. And it's okay to kind of sit in that discomfort. So math, the science of math or the field of math is essentially heading into these unknowns and trying to use logic to make some sort of discovery, right? It's um, taking these ideas, these observations to to somehow discover things beyond like our typical scope. I am not going to claim to have that deep of an understanding. I only have my master's degree in math, and uh, I remember going to plenty of talks during my program and having no idea what people were talking about because there's so many different areas within math that you can go into. You can start exploring, um, and I have a very very limited scope, even as a math professor, of what many people are doing. So, a super quick note. I don't know a lot about quantum mechanics. I know that a lot of people love it. I don't know a lot about string theory, but I know a lot of people love it. But this is something that has just blown my mind, and I can't really understand it. But if you are more interested in it, Google some sort of string theory partial summation, or I give the name of the thing below. But so if you sum the natural numbers as a partial sum, meaning just add up integers from one up to some number n. So 1, 2, 3, 4 up to n. It adds up to n times n plus 1 over 2. So for example, if n is 5, 1 plus 2 plus 3 plus 4 plus 5 is 15. This formula here is just saying it would be 5 times 6 divided by 2, and that is true. So you can prove this is true. Math is in mathematics induction. If you remove the upper limit and you add the infinite natural numbers, so in most mathematics, we would say, well, that limit doesn't exist. You're adding more and more and more, so it should be zero. Within the field of string theory, somehow if you remove that upper limit and you add all of the natural numbers an infinite number of times, so you make it to infinity somehow, you've made it to the end, which again, in our limited brains, I want to be like, you can't do that. But at some point, somebody was like, you can't do that when you take the square root of a negative number. And now we have complex numbers. So who am I to say that this doesn't make sense? I believe it's used in actual string theory uh, textbooks, even. Ramanujan summation. You can look it up. You can see some wild YouTube videos where they show this. Um, and it is just absolutely bonkers that you can add an infinite number of things getting larger and larger, all positive, and somehow end up with a negative fraction. So I just barely again scratched the surface of what I thought was really interesting about math and spirituality. There's tons more that you could look into. Probability theory, I think, is very, very interesting. The history of it in particular. Sacred geometry rears its head a lot in spiritual practices, fractals, sacred numbers, um, the golden ratio, significance of 108 in Buddhism. Lots of mathematicians have very spiritual backgrounds. Pascal is very famous for having this Pascal's wager, which is essentially saying if there is basically a logical argument for agreeing that or for being religious, if there is a God and there is a hell, you sure as heck want to be on the side of God if you if there's not one and you like act as if there is, there's not really a downside. So the argument being you should believe in God because you can make the little table and it makes sense. Anyways, Pascal was a very, very religious, spiritual mathematician, and many other mathematicians were as well. So here is finally the proof that root 2 is irrational if you're curious. I'm going to just kind of flip through this so that you can pause, you can read it if you want. Basically, you make the assumption that if square root 2 could be rational, you could write it as a fraction. Um, so you write it as a fraction, and you basically prove by contradiction, right, write it as the simplest fraction, the smallest possible fraction, the reduced fraction. So 1/2 is a reduced fraction, where 2/4 is not, because you can simplify it down to 1/2. So what you can do logically here, going through this argument, is basically saying, if I could write the square root of 2 as a fraction, write it as the simplest fraction, and you can find a factor of 2 in both the top and the bottom, meaning it uh, wasn't actually the simplest fraction, which is a contradiction, right? We assumed that it was the simplest fraction. Then we found that it wasn't the simplest fraction. So this means that our original assumption that it could be written as a fraction at all um, had to have been false, meaning square root of 2 is irrational. It is a number that cannot be written as a fraction. So thank you so much for listening. I hope that you found some of it interesting. Maybe you learned a little bit. Maybe you have a new appreciation of math, or maybe a new appreciation of spirituality. I don't know. Or maybe nothing at all. Doesn't matter to me. I just did this for fun because I think it's interesting. All right. Have a good one.